Take an electrical bell and an airtight bell jar. The bell is suspended inside the airtight bell jar. First, press the switch for the bell and you will be able to hear the bell clearly. The bell jar is connected to a vacuum pump as shown. Now, start to pump the air out of the jar gradually. You will hear the sound becoming fainter, although the same current is passing to the electric bell. Soon you will notice the less air is left inside the bell jar, the less the sound becomes. If the air is removed completely, you won't be able to hear any sound. From this experiment, we can understand that sound cannot travel through vacuum.
Okay, in this demonstration we're going to look at longitudinal waves. Most of the diagrams of waves you've seen so far have probably been transverse. This is the classic sine wave that gets drawn on the chalkboard up and down and back. And that's a useful diagram, but it doesn't illustrate very well how sound propagates through the air. Sound propagates through the air as what's called a longitudinal wave. So sound is not going up and down. Sound is propagating through the air through air molecules that, if you can imagine all the molecules in the air here, running into each other. So those molecules get compressed and then rarefacted, and then compressed and then rarefacted. The molecules themselves do not travel through the air. They stay where they are. They just bounce off the thing next to them, and that one bounces off another one and bounces off another one. What we have here to demonstrate this is essentially a slinky suspended in a cage. And if you could imagine each little wire of the slinky representing an air molecule, what I'm going to do is start vibrating one end of the slinky, and you can see that the one wire bounces off another, that bounces off another, and ultimately propagates that energy down the length of the spring. This is what's called a longitudinal wave. And this is a much closer example of how sound propagates through the air. Keep in mind, though, that sound propagates equally in all directions. So sound is not a running column going through the air. This is happening in a 360-degree sphere. But if you can keep in mind that this is how the sound actually propagates through the air, it will help you as you end up staring at all of these diagrams of sine waves that are inevitable, even through the material that we will show you. Keep in mind that sound is not going up and down. It's actually traveling longitudinally like this. And that'll help you keep straight the physics involved in sound and wave propagation in the air.
Transmission of sound. Every sound is produced by a vibration. Vibration is the back and forth movement of an object. As you speak, vibrations are produced by the vocal cords in the throat. You can hear only when the sound energy reaches your ears. But how does sound energy travel? Wonder how that works? Come, let's go across to Dr. Zook. Sound energy travels in the form of sound waves. There are mainly two types of waves, transverse wave and longitudinal wave. Let us see how waves travel. We can use a slinky spring to observe both types of waves. Emily is holding one side of the slinky, while Dr. Zook is holding the other end. With a quick upward flick of the wrist, Dr. Zook has sent energy traveling through the slinky. Notice how the slinky moves? This is a transverse wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. The wave traveled from Dr. Zook to Emily and back. Now let's see what a longitudinal wave looks like. Emily is holding one end of the slinky, while Dr. Zook is pulling its other end towards himself and then pushing it towards Emily. Watch closely and you will notice that some of the coils crowd close together and then slowly move farther apart. This is because the vibrations are parallel to the direction of the wave. If the wave moves from right to left, then the particles also vibrate from right to left. This is a longitudinal wave. Sound waves are longitudinal waves. These waves travel at different speeds in different mediums. The medium could be a solid, liquid, or gas. Now let's see how this works. In a solid, the particles are very close together. Sound energy moves as one particle hits the other particle. With the particles being so close together, sound travels quickest through a solid. If we look at particles in a liquid, they appear to be slightly further apart when compared to solid. Thus, sound energy takes a little longer to travel through a liquid. Look at the particles of gas. They are spread out, and hence, sound waves travel most slowly through them. Now we know how sound travels in different media. The vibration of particles produces waves. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Sound waves travel in all directions.
Emily?
Sound gets reflected. That is, it bounces back on hitting a solid surface. Bouncing back of sound is called echo. Bouncing back of sound is purposefully used in detecting depth of seabeds. That's amazing, isn't it? Summary: every sound is produced by a vibration. Vibrations are produced by our vocal cords when we speak. There are two types of waves, transverse wave and longitudinal wave. In a transverse wave, the particles vibrate at a right angle to the direction of the wave. In a longitudinal wave, vibrations are parallel to the direction of the wave. Sound waves are longitudinal waves. Sound travels quickest through a solid. Wavelength is the distance between two consecutive compressions or rarefactions. The number of waves passing through a point in a second is called frequency, and it is measured in hertz. Bouncing back of sound is called echo.
Transverse waves are waves in which the vibrations are at a right angle to the direction of wave motion. Light, the vibrations of a plucked string, and water waves are all good examples. Let's look at a water wave. The wave travels from left to right, and the vibrations are up and down. The vibrations are said to be moving in a transverse direction to the direction of motion. If we look edge on at the wave, we can see that the up and down vibrations are symmetrical about a center line. The maximum distance the vibration moves away from the wave center line is called the amplitude of the wave. The amplitude essentially tells us how noticeable the wave is. For water waves, you would hardly notice a wave with a 1 mm amplitude hitting you. However, a 10-meter wave would grab your attention. The situation is similar with light. The amplitude of the wave tells us how bright the source is. In fact, the amplitude is related to the power that the wave carries. It is reasonably obvious that the wave is regular in shape. This means you can identify a section of it that can be repeated end to end to make up the whole wave. If you measure the length of this small repeating section of the wave, then you have measured the wavelength of the wave. Remember that the wavelength is the length of a section length that when placed end to end gives the whole wave. Now let's unfreeze the wave and let it move again. The wave is moving from left to right at a constant speed. This is called, rather obviously, the speed of the wave. The speed depends on the type of wave and what it is travelling through. For water waves, for example, waves travel faster in deep water than they do in shallow water. This effect leads to tsunami waves. Imagine that I stand in a fixed position and count how many peaks pass me in a given time. I might, for example, count 20 peaks in 10 seconds. I can then ask, if 20 pass me in 10 seconds, how many would pass me in 1 second? The answer is 20 divided by 10, so 2. I can say the frequency of peaks passing me is 2 per second. This is the frequency of the wave. It doesn't matter whether you count peaks, troughs, or somewhere in between, as long as you count the same part of the wave every time. Now imagine I have two waves of different wavelengths, but moving at the same speed. If one wave has twice the wavelength of the other, then the frequency of peaks on that wave passing a point will be half that of the other. So frequency and wavelength are related properties. In fact, the frequency can tell us how long it takes for one wavelength to pass. A frequency of 2 per second means that each wave takes 1/2 of a second to pass a point. We know how long the wave is from the wavelength, so we know the distance travelled in this time. From this we can work out the speed of the wave as distance travelled divided by the time taken. This turns out to be equal to the frequency of the wave multiplied by the wavelength of the wave.
Sound travels at about 760 miles per hour, or 340 meters per second. That's about 661 knots on an average day at sea level. And sometimes you can almost see it. Going close to that speed through air can cause some unusual visual effects. What you're looking at here is a NASA image of an SR-71 bending light waves from the pressure differentials it's producing. Air's pressure and temperature both drop when airspeed increases. Rapid changes in density can be enough to bend light like a lens. How does it happen? Airspeed increases as it flows over the form of an aircraft, pushing its way near Mach 1, the speed of sound. That means that even aircraft slower than the speed of sound can accelerate the air moving over them beyond the speed of sound. As pressure all around the aircraft drops, that air cools, and as air cools, its ability to hold moisture drops. So if there's enough moisture, you'll see it form in clouds that appear attached to the aircraft itself. But the cone-shaped clouds you see aren't in fact traveling with the aircraft. Each section of air is spontaneously reacting to the temperature and pressure change induced by the aircraft's body sliding past. Then there are the shock waves. Shock waves are formed by the air that can't get out of the way fast enough, forming a pressure wave. We perceive that pressure wave as sound. Aircraft actually usually produce two booms. They just reach us so quickly in succession that we can't distinguish the two. All of these factors are quite normal and have come to be expected in images that capture supersonic, transonic, or even near supersonic flight. But on rare occasions, we do get a glimpse of something special. At Kennedy Space Center on February 11, 2010, an Atlas rocket launched into ideal conditions for showing off shockwave. And this is the result. We hope you've enjoyed this little tour of visual and auditory speed of sound phenomena. Visit avweb.com for aviation news and inside information for pilots. This has been Glenn Pugh for avweb.com. Thanks for watching.